To introduce the subject of logarithms, it's helpful to look first at the common logarithm. The common log has base 10, so it's the inverse of the exponential function with base 10. The exponential function with base 10 is this one here, f of x equals 10 to the power x. So let's just fill in some values for the exponential function first. We'll start with the easy ones. If x is 1, then y, or f of x, is 10 to the power 1, which is just 10. If x is 2, then f of x is 10 to the power 2, which is 100. And if x is 3, y is 10 to the power 3, which is 1000. Anything to the power 0 is equal to 1, so that's 10 to the 0. 10 to the negative 1, this is where I'm going to take a reciprocal. The power negative 1 causes me to take a reciprocal of the base 10, so I get 1/10. 10 to the negative 2 causes me to take a reciprocal and square it, so that gets me 1 over 100. And similarly, 10 to the negative 3 causes me to take a reciprocal and cube 10, so that's where we get 1/1000th. Remember that we can find the inverse of a function by just swapping the input and output variables. So finding this inverse numerically is very quick. All we have to do is copy our numbers down, but in the other order. So now my inputs are going to be these numbers: 1 over 1000, 1 over 100, 1 over 10, 1, 10, 100, 1000, and the outputs are going to be the powers that I would raise 10 to get these numbers. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. To evaluate a log, we can think about the relationship between a log function and an exponential function this way. If I want to evaluate log of x equals, and to figure out what goes in this box, then it's the same thing as asking myself what would go in this box. If the base is 10, what power would I raise 10 to get that value x? So for example, looking at this first question, log of 100, I'm going to phrase that to myself as, okay, I'm trying to figure out what goes in this box. It's the same thing that would go in this box. 10 to what power equals 100? Whatever the answer is to this is also the answer to my question, what is the log of 100? Well, I would square 10 to get 100, and so the answer to this is 2. Same idea here. I'm trying to find the log of 1 over 1000, so I'll ask myself 10 to what power gets me 1 over 1000? And I have to think about this in 2 steps. One step is that it has to be a negative number. That's how it turned into a fraction, right? I would take the reciprocal of this 10 if I had a negative power. Then I ask myself how many zeros, right? Because that tells us what overall power of 10 we have with or without the reciprocal, and that's 3. So it looks like I would raise 10 to the power negative 3 to get this, and therefore the log of 1 over 1000 is equal to negative 3. So keep in mind that when we're evaluating a log, it's the same thing as asking ourselves, if I know the base and I know the result, what is the power? So the result is always an exponent. Finally, we ask ourselves 10 to what power is equal to 1? And we say, write anything, doesn't matter what the base is, any number to the power 0 is equal to 1. So the log of 1 is equal to 0. We can look up at the chart that we just filled in and see that these results that we got using this new rule match what we see in the table. Our first one was that the log of 100 is equal to 2, and we can see that here. If the input is 100, the output is 2. Our second is that the log of 1 over 1,000 is equal to -3, which we can see in our first data point. With the 1 over 1,000 being the input, the output is -3. And our last one, log of 1 is equal to 0. Looking at this ordered pair here, with input 1, we have output 0. So this is the same information again. It's just looking at a way to evaluate logs without having to first fill out a table for an exponential function and then swap the rows. So a very common application of logarithms is the decibel scale. And log scales are used when we have to work with a huge range of numbers. So for example, if we're measuring sound intensity in watts per square centimeter, then the range of values that we have to work with go from 10 to the -16 to 10 to the -4. All of these are very small numbers, but we can see that it's also really a huge range, and they're not numbers that are easy to work with. For example, something in this range might be 0.000000516. So trying to compare this number to 0.0000328, they both just look tiny to our perception, and it's kind of hard to work with these numbers. What the log allows us to do is to just look at essentially what the exponent is on that 10, so that we can just get a little bit more of a sense of what these numbers are. We humans do really well on scales that go approximately from 0 to 100. So if we can take a normal range and somehow apply a mathematical function that will spread that range out over 0 to 100, then we do much better with it. So this is the formula we use for decibels. D of x is equal to 10 times the log of 10 to the 16th times x. So x, our input, is sound intensity in watts per square centimeter. We multiply it by 10 to the 16 so that we get these numbers all up to closer to 1, right? And then we take their log so that we can separate them more easily and multiply by 10 just to get it to a scale that's approximately 0 to 100. So let's have a look at some of these examples here. If my input is a sound intensity of 10 to the -12, then I want to know what is d of x, right? So what is d of 10 to the -12? Well, that's going to be 10 times the log of 10 to the 16 times 10 to the -12. So the first thing I need to do is just use properties of exponents to work on this part here. So I would add those powers and get 10 to the +4 for that part. Now this is still inside of a log, and it is still multiplied by 10. So now the next step is to evaluate the log of 10 to the power 4. Well, remember that the way we do that is we say 10 to what power is 10 to the 4? Well, this one is really quite obvious once we get used to evaluating logs, right? This has got to equal 4, because 4 is the power I would raise 10 to in order to get 10 to the power 4. It really is that simple. So I now have 10 times 4, which we can see is 40. So we've taken this number 10 to the -12 and we've converted it to a much more reasonable number for our perceptions, which is 40 decibels. So we can do the same thing with 10 to the -8, and in fact all it's going to take is a little bit of reworking of the numbers that we already calculated. So let's go ahead and modify this to handle 10 to the -8. When I multiply these now, I'm going to get 10 to the positive 8. The log of 10 to the 8, by the same kind of reasoning, is going to be just 8. And 10 times 8 gives me 80. So it's easier for us to compare numbers like 40 and 80 and see that the 80 seems much louder than it is for us to compare numbers like 10 to the negative 12 and 10 to the negative 8. So that's what the log scale does for us. It brings numbers that would not be very comfortable for us and that would be difficult to compare to a scale that's very comfortable.